Hello everyone, today we are going to see the fourth lecture of this course. The title of this today's lecture is Synthesis of Nanomaterials by Biological Methods. So in the previous lecture we have seen how to synthesize nanoparticles by physical method and chemical methods, and in this lecture we are going to learn how to synthesize nanoparticle by biological method, and also we are going to learn why we have to use biological methods, what are the advantages of using these biological methods, and what is the mechanism behind the synthesis of this nanoparticle by biological method. And we are also going to see viral nanotechnology. In this we are going to see how to use virus and make use of those virus nanostructures for various applications. So first we see what is biological synthesis. It is a green method. It is similar to your chemical synthesis method only, but in this case we are not going to use the chemical reducing agent. Instead of using the chemical reducing agent, we are going to use microbial enzymes or plant phytochemicals. So this is a overview of biological synthesis of nanoparticles. So here we are going to use either microorganism or plant tissues, and the enzymes present in the microorganisms will act like a reducing agent as well as it act like your stabilizing agent or capping agent. So similarly the phytochemicals act like a reducing agent and it also act like a capping agent for your nanoparticles. So when you mix this bacteria or any microorganism with the metal salt, so the enzymes will convert these metal salts into metal nanoparticles. So these nanoparticles can be further purified and characterized. So by using this scanning electron microscope, transmission electron microscope and various other methods, we can characterize these nanoparticles. So the characterization of nanoparticles I will explain in the next lecture. So once you characterize these nanoparticles, you can do the biofunctionalization. That means you are going to add functional group to these nanoparticles and we can take it for further applications. Why to use biological method? What are the advantages of using this biological method? So here we are not using any toxic chemicals, so it is a eco-friendly nanoparticles and it is economically viable because we are not using any costly chemicals, we are using the plants or microbes which is readily available, and easy to tailor the size or shape and nature of the nanoparticle by simply modifying the culture conditions like pH, temperature or the nutrient media. So these are some of the examples of nanoscale structures in the nature. So this is a monothetic bacteria producing magnetic nanoparticles, and also diatoms synthesize siliceous materials, and also multicellular organisms produce hard inorganic and organic composites. Examples are bones, shells and spicules. So these are the some of the examples which is having nanostructures in the nature itself. So let us see some example using bacteria how we can synthesize these nanoparticles. So the bacteria are considered as potential biofactory for the synthesis of nanoparticles such as gold, silver and other metal nanoparticles. So this bacteria can produce the nanoparticles either intracellularly or it can produce extracellularly. So what is intracellular? Intracellular means inside the cell. What is extracellular? It can synthesize nanoparticle outside the cell. Okay. So let us see some examples. The Pseudomonas bacteria, they are isolated from silver mines. So it has the capacity to convert the silver nitrate into silver nanoparticles, and it is synthesizing the nanoparticles in the periplasmic space of bacteria. So from this you can get an idea. So you can also collect some soil sample near the copper industry or some other metal based industry. So those soil samples may have some bacteria which can convert your copper into copper nanoparticles. Another example is Morganella species bacteria. So they isolated this bacteria from the insect midgut and it is able to secrete nanoparticles extracellularly. And we can also use yeast for making the nanoparticles. For example, the candida can be useful for synthesizing cadmium sulfide nanoparticles, and also recently the yeast strains have been identified for making gold nanoparticles and other metal nanoparticles. Using the yeast we can have a controlled size and shape of nanoparticles can be easily achieved, and again you know the yeast is not very costly, it can be available in any shops. You can purchase the normal yeast and you can do your research. You can simply add this yeast, grow it in the presence of your metal salt. So the enzyme present in the yeast can convert your metal salt into metal nanoparticle and you can do further characterization and application studies. And we can also use the fungi. The example is Verticillium species. So that can be useful for making gold nanoparticles with very good mono dispersity. Okay. And also why we have to use fungi, because the fungi are known to secrete much higher amount of proteins, so thus might have high significant and higher productivity of nanoparticles in this biosynthetic approach. And we can also use plants. So the quantum dots, it is a fluorescence nanoparticles, semiconductor nanoparticles. So the quantum dots have wide application in nanobiotechnology, and we can use the plant as a good source for synthesizing these quantum dots. So for example, the alfalfa roots, it has the capability observe the Ag0, the nanoparticle Ag0 it can observe and from agar medium, and it can transferring them to shoot of the plant in the same oxidative state. And also we can use geranium leaf extract, and this can convert silver ions to the silver nanoparticles. In addition to that, we can also make silver gold bimetallic nanoparticles using indica leaf extract broth, so which can be useful for synthesizing these bimetallic nanoparticles extracellularly. So similarly, there are plenty of examples are available. We can use any microbes or any plant, and we can make the metal nanoparticles or any kind of nanoparticles. So this tabular column will give you an idea which bacteria we can use and which metal nanoparticle can be synthesized, whether it is intracellular or extracellular, and what is the size range of these nanoparticles. So this is a plant and plant extracts. So you can use this kind of plant extracts. For example, aloe vera, you can use it for gold nanoparticle, and it synthesizes extracellular, and the size of the nanoparticle is 50 to 350. So similarly, we have plenty of researches going on in the biomedical or biosynthesis of nanoparticles. So let us see another example where we are going to see how we can use magnetotatic bacteria for synthesizing magnetic nanoparticles. So this magnetotatic bacteria are a heterogeneous group of prokaryotes, and they orient and migrate along the geomagnetic field lines. It do not have any flagella, it moves according to the geomagnetic field lines, and its migration is based on the intracellular magnetic structure. So the intracellular magnetic structure is called as magnetosomes. So the magnetosome means it is a membrane bound magnetite particles. So this is a structure of this is bacteria, you can see here. So Fe3 place is we have to add to this bacteria, and this will convert into iron oxide nanoparticles. So how to grow this bacteria? So we can grow this bacteria in the agar plate and transfer it to the test tube and grow it overnight, then you transfer to the broth, LV broth in a conical flask. And once the bacteria is grown, you have to add the metal precursor. We have to filter sterilize the metal precursor and add it to this in a 2:1 millimolar ratio. So when you add it, then you have to incubate in the incubator at 37 degrees Celsius for 200 rpm, and finally you will get the iron oxide nanoparticles, which we can take it for further characterization. So here you can see the beautiful pictures of these magnetosomes which having these magnetic nanoparticles. And another advantage of this magnetic bacteria is we can assemble these magnetic particles by applying external magnetic field. By simply applying the external magnetic field, we can arrange this magnetic bacteria. So after assembling the bacteria with the micro electromagnets, what we can do is we can remove the cell membranes. How we can remove the cell membranes? We can add some lysis solution, so that can lyse the cell membrane and it can leave the nanoparticle as intact. So this picture will clearly tell you. So this is a scanning electron microscope picture of magnetic structures assembled after removing the cell membrane of the trapped bacteria. So they assembled this bacteria in such a way, like a chain structure or like a ring structure. Once the bacteria is assembled, they added the lysis solution. So this lysis solution will degrade the cell membrane and leave the magnetic nanoparticles intact. So in figure A you can see here, it is a single chain of magnetic nanoparticles along with the cellular debris. These are the lysed cellular debris, cell membrane debris. Okay. So and again you can see that there are two small nanoparticles indicated by this arrow. So these are still attached to the chain due to the magnetic field from the adjacent large particle. And this is a long chain from a single bacterium, and this is a ring of magnetic nanoparticles formed by trapping and lysing two bacteria. And let us see the overall mechanism of synthesis of nanoparticles. So here The widely accepted mechanism of synthesis of silver nanoparticle is the presence of enzyme called nitrate reductase. As you know, this nitrate reductase is an enzyme in the nitrogen cycle which is responsible for the conversion of nitrate to nitrate, and during the catalysis the nitrate is converted to nitrite and an electron will be shuttled to the incoming silver ions. So this is well studied in the Bacillus microbes. So this Bacillus microbe is known to secrete cofactors like NADH and NADH dependent enzymes. So this will be converting this Ag plus to Ag0 and to the formation of silver nanoparticles. So this animation will give you an idea. The silver nitrate is converted into Ag plus, and this nitrate reductase enzyme and this NADH, it is going to convert this Ag plus to Ag0 silver nanoparticles. So let us move on to the another topic of this lecture, that is viral nanotechnology. So previously we have seen how to synthesize nanoparticles using bacteria, fungi and also plant based extracts, and here we are going to see how we can use this virus for making various nanostructures, and it could be have wide applications. So let us see a small animation. So this is a viral infection and replication cycle of retrovirus. So from this animation you can understand how the retrovirus come and bind to the mammalian cells and how it is going to replicate. See, the first step is attachment of virus to the mammalian cells. So once it attached, this nucleic acid is releasing the nucleic acid, and the nucleic acid is made copies, and this nucleic acid is going and integrating with the mammalian cell genome. And it is making multiple copies of the viral genetic material. And using that viral genetic material, whether it is a DNA or RNA, it is making the proteins which is required for making the complete virus structure. So the synthesis is done. So once the synthesis is done, it is packing, okay, and packing and releasing the viral materials. So a single virus particle is entering into a cell and it is making millions of copies of virus, and finally it is destroying the complete cell, okay. So this is a typical viral replication cycle. So from this we can understand like which are the components important for the viral infection and replication. So let us see how we can use this virus structure for using it for various applications. So this is a viral capsid. So you can simply call it like a protein box. So it is made up of protein, and as you know, the size of all the virus is in the range of nanometer, and the main important component of any virus is its genetic material, either it is a DNA or RNA. So once we remove this genetic material, DNA or RNA, it will be like a simple nano sized protein box, and we are going to use this nano sized protein box for synthesizing various nanomaterials, and also we can use it for various therapeutic as well as other applications. So instead of nucleic acid we can put our anti-cancer drug, or you can put a imaging agent for diagnosing various diseases. So thus we are converting the normal virus for various applications. So let us see what is viral nanotechnology. So the viral nanotechnology is an emerging field. It is a highly interdisciplinary field, where we make the viral nanoparticles and we can use it for applications in various areas, for example electronics, energy, as well as next generation medical devices. Okay. And here we are going to use that viral nanoparticles, and we can tune the viral nanoparticles, like we can program these viral nanoparticles, we can easily modify it using the techniques like bioconjugation chemistry, encapsulation techniques, and mineralization strategies, and also film and hydrogel development. We will see one by one in the subsequent slides. So here the viral capsids devoid of their nucleic acid genomes can be thought as a nano container. As I told you earlier, the viral capsid without the genetic material, it can be used as a kind of nano container. So again the scientists got the idea from the nature. It is a biomimetic approach for making the nanoparticles. So we can use a protein cage architecture, and it can act like a size constrained reaction vessel. So this protein cage will act like a reaction vessel, and it can synthesize nanoparticle in the smaller nano size vessel. So this is a schematic representation of protein cage, and so this is a protein cage architecture. It is our viral capsid. You can assume this structure to correlate with the football. Okay. So you can see here it has a interior subunit interface as well as exterior. So in the interior we can add any kind of therapeutic molecule, we can add any anti-cancer drug or any other therapeutic molecule, and in the subunit interface we can add gadolinium metal ions. So this will be useful for imaging application, we can use it for cancer imaging, and again in the exterior we can add RGD peptides. These are small peptides made up of arginine, glycine, and aspartic acid. So this is a 3 amino acid peptide, so which will enhance the cell attachment. So a single nanoparticles having multiple function. So this is called as multifunctional nanoparticles. So it can be having a therapeutic value, and it is having this imaging application, and also it is cell specific targeting. It can easily bind to the cell using these RGD peptides. And in this case viral nanotechnology, we are going to use only the plant virus, we are not going to use the animal virus. So why we have to use plant virus? So scientists have engineered viral nanoparticles from plant virus, insect virus, and animal virus, but they avoid the human virus, because when you use the human virus it will induce immune response or any kind of toxic side effects. So in order to minimize those chances of virus interacting with the human proteins, so they are using the plant virus. And another important thing is, if you want to make the animal virus, you have to use the animal cells. Again the cost of the virus will be high, as well as in some cases you have to sacrifice the animal to isolate the virus. But in this case it is very easy to produce in large quantities. You are going to add the virus to the plant leaf, and this plant leaf is going to make n number of millions of virus. Okay. And another advantage of using the plant virus is it can hold 10 cubic nanometers of particles. So the size of the plant virus is bigger, and so that we can load more amount of anti-cancer drug or any kind of therapeutic molecule inside the plant based viral particles. And another advantage of this plant virus is, you can see these are all our plant virus. Okay. So all the names like TME means tobacco mosaic virus. So similarly all the names of virus is mentioned here, and if you see that the plant virus have different size and different shape. So it depends on the application, you can select the plant virus and take it for further applications. And this is a complete viral nanotechnology assembly line. So if you want to make the viral nanoparticle, the first step is you take the plant virus, add it to the plant leaf. So it is going to make millions of copies of plant virus, and purify the plant virus. Once you purify the plant virus, the second step is you have to chemically modify it. Okay. How do you modify that? You have to remove the nucleic acid from the plant virus, and you can put your therapeutic molecules, and also you can add some kind of ligand, so that it can go and specifically bind only to the cancer cell, not to the healthy cells. So once you done with this, you have to evaluate this efficiency of this nanoparticles. So how do you evaluate? You have to use the in vitro and in vivo. So what is in vitro? In vitro means in lab condition. So we can use the cell lines, mammalian cell lines and you can study the therapeutic efficiency. Once you have studied and optimized the concentration, then you can take it to the animal models, that is in vivo. In vivo means inside the living system. So we can use the mouse model or any other animal models and we can study the therapeutic efficiency of your viral nanoparticles. And we can also use this protein cage for inorganic nanoparticle synthesis. So the beauty of this virus is the exterior and interior of this cowpea motile virus CCMV, this viral capsid have a distinct environment. The interior surface is more partially charged than the exterior. So this will allow and serve as a nucleation site for crystal growth. So as I told you in one of second lecture, so nucleation is very important process for nanoparticle synthesis. So after the nucleation, the size and shape of the mineral are defined by the interior of the viron, and it can make a nanoparticle of maximum size of 24 nanometer, and also it can make a uniform size nanoparticles. So another important property of this CCME viral capsid is it has the property of gating. So what is gating? It is a pH dependent structural transition, that is called as gating. So if the pH is greater than 6.5, there will be a increase 10% increase of viral dimension, and it can easily allow the any materials to go inside. And the next one is we can encapsulate artificial cargo within the viral nanoparticles. So as I told you earlier, the viral capsid have many functions, okay. So one of which is to protect the virus genome, and all you know, this virus genome or any genetic material like DNA, RNA, it has the negatively charged, okay. So we can make such kind of nanomaterial which have the negatively charged, and so that this virus can easily encapsulate those negatively charged material into the viral protein capsids, okay. And this pores in the capsid structure allows small molecule to diffuse between the external medium and capsid interior. And next one is artificial polymer. As I told you that the viral nanoparticles having genetic material, and again the genetic material is DNA or RNA, any genetic material like DNA or RNA, it will be negatively charged. So we can make a similar kind of polymer which will have the negatively charged. So this is our polymer which is negatively charged, at the same time it is carrying the anti-cancer drug. So it acts like a artificial nucleic acid and it will be packed inside the viral structure. So here we can see here how we can encapsulate the materials during particle self assembly. So as I told you earlier, so here we can take the plant virus. For example, we can take the plant virus from hibiscus ring spot virus, okay, and the first step is you have to remove the nucleic acid from this virus. Once you remove the nucleic acid from the virus, and the second step is you have to encapsulate the polyacid and doxorubicin. The doxorubicin is an anti-cancer drug and polyacid is a negatively charged polymer, so which will resemble like your nucleic acid of the particular virus. So what happens is during the self assembly, instead of it will take this artificial polymer which is having the anti-cancer drug, and it will pack this polymer into this viral capsid. And again we are going to add folic acid to this viral coat protein in the step B1. So when you add this folic acid, it will be targeted only for the breast cancer. So mostly the breast cancer cells express folic acid. So breast cancer cells express receptor for folic acid. So when you make your nanoparticles with anti-cancer drug, and when you are adding a molecules folic acid, so it can go to the cancer cell which is having receptor for folate. So it can go and specifically bind only to the breast cancer cells, not to the healthy cells. So we can make a targeted nanoparticles for cancer therapy using this virus nanoparticles. And next one is size dependence. So we can use this virus as a size constrained vessels for making different size nanoparticles. Okay. For example, here you can see here these are different types of virus and each comes with different kind of size. So when you synthesize nanoparticle, you will get a uniform size. At the same time, based on the viral capsid protein size maximum capacity, it will make the different size nanoparticle. For example, you are having 2 or 3 types of plant virus. So one is 5 nanometer size, another one is 10 nanometer size. So when you synthesize nanoparticle using this virus, it can make 5 nanometer particle and it can make 10 nanometer particle. So it can make a uniform size nanoparticle. Here you can see here all the virus particles are very uniform size. So you can make a uniform size particle, at the same time it acts like a size constrained vessel to make the small size nanoparticles. And also this viral scaffold act like a template for material synthesis. So what is biotemplating? It acts like a template. It is a process that mimics the biomineralization. That means formation of inorganic structures by the proteins. So here we can take the example of rod shaped tobacco mosaic virus. It will infect only the tobacco plant, and also filamentous N13 phages. That means it will infect only the particular type of bacteria. Okay. So we can use this as a template, and we can make a semiconducting nanotubes or nanowires which could be useful for next generation electronics such as data storage device or battery electrodes. So let us see how we can use it. So this TME virus is a highly versatile virus because it has a external surface and internal surface, and both the external surface and the internal surface, it has a capacity to mineralize. Okay. So the interior is only 4 nanometer, and again we can deposit broad range of materials on this TME. For example, you can deposit semiconductor nanocrystals inside the TME, and outside you can coat with the different kind of metal nanoparticles. So as I told you earlier, so this TME is a rod shaped virus. So it has a different kind of exterior and different kind of interior. So based on that, we can deposit various types of metals inside and another kind of material on the exterior environment. So it can act like a kind of nanotubes and nanowire. So here you can see here, this is an electron microscope picture of this tobacco mosaic virus. So we can use it for electroless deposition. Okay. So we will be using this virus particle, and we can add this PD on the top, and inside we can add the nickel. It is filled with the nickel, and this is in this figure they add the nickel on the external surface. So if you combine two metals at the nanoscale, it will give a very good different kind of new properties, some novel properties it will express. And we can also enhance this biotemplating property by genetically engineered virus. So genetically engineering means you are modifying the genetic components like DNA or RNA of the virus, and you can modify it. For example, if the virus is expressing this kind of peptides, so that is more specific for the silver. So suppose for example, if your virus is expressing this kind of peptide sequence, it is more specific for the silver nanoparticle, and if your virus is expressing this kind of peptides, it is more specific for the gold. So we can modify the virus by genetic engineering, and we can make it for further applications. And also we can use this virus as a scaffold for 3D cell culture. Okay. So I will explain you what is 3D cell culture. So here we are going to use the TME plant virus, and it will be displaying the arginine glycine aspartic acid, that is RGD peptide, which I explained in my earlier slides. Okay. So that will promote the attachment of cells more effectively. Okay. And we are going to incorporate a non-toxic magnetic nanoparticles within this virus to create a system of cellular leviation. So where you can grow the cells in the 3 dimension, and it will exactly mimic your body condition. So usually in the lab we grow the mammalian cells or cancer cells in 2-dimensional petri dishes. So usually these cells attach to the bottom of the petri plates and it grows nicely. But again, when you see this inside our body, we have all the organs are 3-dimensional. So when you have the 3-dimensional environment or 3-dimensional cell culture, we can study the efficiency of drugs and we can correlate with the animal model studies. So we can use a viral nanoparticle for making the 3D cell culture. How we can make it? So we can make use of viral particle, okay. So we can take the virus, and again it is not the tobacco mosaic virus that will be rod shape, it is just to give an idea. So in this viral virus we are going to add our non-toxic magnetic nanoparticles. So when you add these nanoparticles and this virus having RGD peptide, so this RGD peptide will enhance the cell attachment. So this viral nanoparticle is coated at the bottom of your cell culture plate, then you are adding the cells. So when you add the cells will bind to this, and when you apply the magnetic field it will elevate. So why it is elevating? Because it is having magnetic nanoparticle inside. So when you apply this magnetic field, all the cells will be lifted, and when you grow the cells in this same condition, the cells will become a 3-dimensional cell culture. So when you add, if you want to test any efficiency of the drugs, so you can add it to this 3-dimensional cell culture. So that will closely mimic your in vivo animal studies. So in this lecture we will learn how we have converted this villain virus which causes infection to a hero virus. So this virus could be useful for making not only for biomedical application like therapeutic, it can also have other applications in electronics and other field. So as a summary of this lecture, so we have learnt like how the biological sensor nanoparticles has opened its door to a world of nanoparticles with easy preparation protocols and less toxicity nanoparticles, and also we have learned what is the mechanism of synthesis, but still more research needs to be done on understanding the mechanism of nanoparticle formation. So once we understand the mechanism of nanoparticle formation, we can still fine tune the size and shape of nanoparticle by simply changing the parameters. And other thing is we can also use the genetic engineering techniques to improve the particle properties, and we can also control their composition. And again the viral nanoparticles could be explored for various therapeutic and diagnostic applications, and it will have applications in various diseases, and as I told you earlier, it is like a multifunctional nanoparticle. I will end my lecture here. Thank you all for listening this lecture. I will see you in another interesting lecture.